All right, this is our last lesson in our logs module. And so today we're going to take everything we've learned and we're going to apply it to real world situations. So we're going to give it okay, so what's the point? So our goal today is to be able to apply our knowledge of exponential growth and decay to real world problems. This is actually going to be review to a certain level of what you did in Algebra 1. And then with Algebra 2, we're going to take it just a little bit further. So this should be mostly review the beginning part. So as we are working through, I need you to be thinking about which variable are you solving for if you have to utilize your knowledge of logs to solve the problem. So as we work through these problems, that's going to be the difference between what we did in Algebra 1 with exponential growth and decay and what we're doing in Algebra 2. All right, so let's get some basic information. Like I said, this should be review of Algebra 1. So exponential growth. So if something is growing, that means it's increasing at a higher rate than 100%. Because if we were maintaining 100% of our students at our school, then we would keep the same amount of students every year, right? But if we have more than 100% of our previous year students, then that would mean that we're growing. So the exponential growth formula is going to be, so it's a function of time, so f of t, where t represents the time, is going to be a, which is my initial amount, times 1 plus r. And the reason that it's plus r is because we're talking about growth. So 1 as a decimal is the equivalent to 100%. So anything like if you think about 99% is 0.99. So 100% is 1. So 1 plus whatever the rate is to the power of t, or time. So it's talking about whatever the initial amount is, and then we have 100% plus whatever that rate is that it's growing by, and we raise that to the time. All right, so we are going to work through some examples. Like I said, this is a review of Algebra 1, so hopefully you remember doing this. We are going to read the problem, we're going to pick out the important information, and we're going to label it accordingly. So when I look at my formula, variables that I can have are f of t, which would be the output. I could have a, which is the initial amount. I can have r, which is the rate, and I can have t, which is the time. So time is the input. How much money I have in the account, given that amount of time, that's going to be my output, depending on my initial amount and the rate. So as I read through, I'm going to pick out the important information and I'm going to label it, and then one of those variables, either f of t, the initial amount, the rate, or the time, is going to be missing, and that's what I'm going to solve for. I'm going to use my algebra skills to solve for that. All right, so let's read through number 1. The original value of an investment is $1,800. So original value, that reminds me of initial amount. So I'm going to label that A. If the value has increased by 7% each year, so 7% is a rate, and rate, if I put 7 into the calculator doesn't have a percent button. So we have to write it in decimal form so it makes sense. So that's going to be a rate of 0.07 because it's 7 out of 100. So if I did 7 divided by 100, that gives me 0.07. So write an exponential function to model the situation and then find the value of the investment after 15 years. So 15 is going to be my time because we're talking about years. And we're looking for, so we want to think about what are we solving for? Find the value of the investment. So that's going to be the output, or f of t, is what we're looking for when time is 15. So let's start with just writing the equation. So I'm going to have f of t, I'm going to go ahead and put it in green, is equal to A, so 1,800 times 1 plus my r, and my r is 0.07. And I'm going to raise that to the t because I'm just writing a general equation first. So that would be my simplified. I could even take it one step further and say f of t equals 1,800 times 1.07 because I can combine those. So that would be a generalized function for this investment. At any given time, I can find the investment. So let's go ahead and use that function. So we're going to say f of 15. We're going to look at what is the output, or what is the value of the investment after 15 years. So 1800 times 1.07 to the 15th power. And so, because my variable, or what I'm solving for, is over here on the left-hand side already isolated, I'm looking for this output, I can literally just type this into my calculator. So when I type it in, I get 4,966.20, well, 0.25677, but we're talking about money, and we know money is to 2 decimal places. So it's really $4,966.26. But that answer has context. So if it has context in my problem, it has to have context in my answer. So I'm going to write a quick sentence. So I'm going to say that the value of the investment after 15 years will be $4,966.26. All right, so what I'd like you to do is pause the video, and I'd like you to get as far as you can with number 2. I do want to bring out something that I want to draw your attention to. So here they told me it was 15 years. Down here, they're saying in 2002, so that's the start of the story, we have this many students, it's increasing by this rate each year, write an exponential function to model the situation, then find the number of students, so think about what am I looking for, which variable am I solving for, enrolled in 2014. So I need to think about how much time has passed from 2002 to 2014. That will tell me my time. So go ahead and pause the video and try this on your own. All right, so hopefully you were able to come up with this function right here. So f of t equals 972 times 1.015 to the t. And hopefully we'll be able to use that function to say that in 2014, there should be about 1,162 students in the school. So if you got that, you can go ahead and move on to the exponential decay portion. If you didn't, I'll explain it now. So first of all, I was able to pick out that 972 is A, my initial amount. I was also able to say that 1.5 is my rate, but we know that in a calculator, I can't put in a percent sign, so we write it as a decimal. And so 1.5 is like 1.5%. So I know it's not going to be 0.15 because that would be 15%. So I take 1.5 divided by 100, or I'm moving my decimal 2 places to the left. So if I move it 2 to the left, it's 0.015. And then I went ahead and said in 2014, so if we started in 2002 and we're talking about 2014, that's 12 years that have passed. So my general function, I just put in the 972 and the 0.015, and I was able to come up with that because 100% plus 1.5% gives me 1.015. And then I was able to take that function, put in 12, and find the output is 1162.14, and we're talking about people, so I can't have 0.14 of a student, Aaliyah, but I can have 1,162 students is my about, and that shows that I rounded. All right, so for exponential decay, so decay means we're getting smaller. So if we were maintaining our school enrollment, we would be having 100% every year of the amount of students from the previous year would be coming the next student. So when we added the rate, it gave us exponential growth because we're getting bigger than we were. But if we are getting smaller, so if we're having a decay in our population, then from that 100%, we would then subtract the rate. So that is the only difference between exponential growth and exponential decay. All right, so we're going to have the formula f of t equals a times 1 minus r to the t. So like I said, it's going to be the exact same except for we're subtracting because it's getting smaller. So if I ever am looking at a problem and the number inside here that's being raised to the time is less than 100%, I know it's decay. If it's greater than 100%, I know it's going to be growth. And that should be review of that Algebra 1 material that we talked about last year. All right, so let's go ahead and apply this to some situations. So an investment of $12,000, so that is my initial amount, is losing value. So losing value tells me that it is decaying at a rate of 4% each year. So this is decay. So my rate is going to be 0.04 because that's what 4% as a decimal. So I'm going to write an exponential function to model the situation, and then I'm going to find the value of the investment. So I'm looking for f of t. So I'm looking for the output when the input is 9. All right, so let's go ahead and write that function. So I'm going to have f of t equals a times 1 plus my r, and I raise that to my t. And so I'm going to go ahead and simplify what's in that parentheses because I can. So f of t is really $12,000. And so 1 minus 4% is going to give me 96%. And I'm raising that to the t. Oh, I messed up. Hopefully you caught that. And that should be minus. All right. So that is my function. And so now I'm going to use that function to predict what the value of the account is when time is 9. So in 9 years. And since what I'm looking for is over here already isolated, I can literally just type this into my calculator. So when I type it into the calculator, I end up with an input of 9 gives me an output of 8310.4080. Oops. All right, so we're talking about money, and it has to be in context, so I'm going to go ahead and write a sentence. All right, so the value of the account after 9 years will be $8,320.41. All right, so go ahead and pause the video, and I'd like you to try example 4 on your own. All right, so for number 4, hopefully you were able to get the 2 parts. This would be your function, f of t equals 35,000 times 0.92 to the t, because it's decay, so this is less than 100%. And we were able to predict that in 2015, the car will cost approximately $19,524.63. If you got that, you can go ahead and move on to our compound interest problems. If not, I'll explain that now. So first of all, I went through and I picked out my important information. So the initial value was $35,000 because that's how much he paid at the start. Depreciate. You should remember that from Algebra 1. Depreciate means to go down. It loses value. So if I appreciate you, then I have more value for you because I appreciate what you've done for me. Depreciate means to go down. 8%, and I know that I can't type a percent sign into the calculator, so that is a rate of 0.08. And we're going to write the exponential model, so I just plugged everything in, and I knew that 100%, and if it's losing 8%, that means it's at 92%. And then I found the value of the car in 2015. Well, if it started in 2008, that means that 7 years have passed. And so when I plug all that into my calculator, I have that sentence putting my answer in context. All right, so that's the first half of our notes is just that idea of basic exponential growth and decay. So I need you to have an interaction. What are you going to need to remember about exponential growth and decay and these word problems? Where were some mistakes you made? What mistakes might you see students make? What are things you're going to need to remember? All right, so we're now going to take this idea of exponential growth and we're going to apply it to a bank problem. So there's this idea of compound interest, which means I'm going to get paid money if I invest my money into a bank account. They will give me a certain percent of what I put in every period. And so they're going to give me, sometimes it's annually, so every year I'm going to get a certain percent of what I invest given to me. And it's kind of like a, hey, come invest in our bank, give us your money to hold, and we'll give you something for doing that. And so every period I get a little bit of more money that's going to go into my account, and that's where this formula is going to come into play. So the formula for compound interest is, all right, so this formula is relatively similar to the one we were just doing, except for adding in this idea of compounding. So using that interest rate multiple times throughout the year. So what we're going to have is you may see it f of t or you may see it a. I know that's confusing. This large A just means account balance. That's all it's really talking about. So how much do you have in the bank at that very moment? I like to think of it still as a function of time. So either way, just as long as you know that those are interchangeable. All right, so it's going to be P now instead of A, but it's the same idea. It's the principal, which in banking terms means how much the person who is putting money in, how much they put in. So it's the amount of money that the actual person is investing. And so it's still going to be 1 plus. And in this case, compound interest is never going to go down. It's always going, if I put money in a bank, I should never lose money unless I take it out. I won't ever lose interest. I will only gain. So it's 1 plus. And then here it's the rate divided by the number of times that it's compounded yearly. And we'll talk more about that. So if I am compounded monthly, that means every month they're going to put interest in my account based on my account balance, then my N would be 12 because that's how many times it would compounded yearly. If it's done monthly over the course of a year, that would be 12 different times. And then that's going to be raised to the N times T. I know that T is a little bit hard to see, but that's what's happening here. So it's going to be the number of times per year times the years that my money is in the bank. So that's what that means right there. So A or F of T equals the principal times 1 plus R divided by N to the N times T. So these are the guiding questions. And I know some of you have been asking me some questions about this, and then when I ask you what the guiding questions say, you don't know. So I don't give these to you because I just want you to write something down. These are supposed to help you think through that process so that when you get stuck, this is your first resource to go to. So I want you to pause the video and write these guiding questions down, and then I will go through example after example after example of using those guiding questions to apply to these math problems. So go ahead and pause the video and write those down now. All right, so let's work through a few examples using those guiding questions. So my first question is, what are the key math terms? And then I'm also going to combine that with what do they represent? So what variables do they represent? All right, so the first problem says Laura deposited $12,000. So just like we've been doing, that's going to be my P. So my principal amount, into an account that earns 8% interest. So that's my rate. So I'm going to write it as a decimal. So 0.08. How much money will she have in 5 years? So that's my time. If the interest is compounded quarterly. So quarterly means fourth. So if it's compounded quarterly, that means that it's 4 times a year. So N is 4. All right, so those are the first two questions. What are the key words and what variables do they represent? So my next question is, which variable is the question asking me to find? So it's asking how much money will she have in the account? So we are looking for A. We're looking for that function of time, the output. So when P is 12,000, when R is 0.08, when T is 5, and when N is 4, how much money will be in the account? So my next question is, how do the variables fit into the equation? All right, so I'm going to take that equation that we were given, and I'm just going to plug everything in. So I'm looking for A, and I want to know when P is 12,000, and it's going to be 1 plus R, which is 0.08, divided by N, which is 4, because it's being compounded quarterly, to the N, so 4, times T, which is 5. So all I've done is I've simply taken all of my information and I've put it into the equation. So then my next question, and this is the difference between Algebra 1 and Algebra 2, is the variable I'm solving for in the exponent? And if it is in the exponent, then I have to use my knowledge of logs. And we're going to look at a few examples like that. If the answer is no, then I just can straight up type this into the calculator because my variable is already isolated. I don't have to do any maneuvering. So I can literally type this into my calculator and get my answer. And then what does my answer mean in context? So in this case, the variable I'm solving for is not in the exponent. I know n and I know t. So I can just type that into my calculator. So when I type that in, I get 17,831.3688 rounded. So then my last question is, what does my answer mean in context? So that's where I'm going to write that final sentence. So after 5 years, Laura will have $17,831.37 in her account. All right, so let's go ahead and look at another problem. All right, so with this one, Jack took out a 6-year loan for $25,000 to purchase a boat at 4.5% interest rate. If the interest is compounded monthly, what will he have paid for total over the course of the loan? So with taking out loans, you end up paying more than what you take out because that's how they make money off of it, is you pay an interest rate for borrowing money from the bank. And so you always end up paying more. So you want to make sure that you think about, okay, what's the interest rate and am I going to end up paying too much over the course of the loan? So this is a great practice in kind of realizing, is it worth taking out that loan? All right, so the first question is, what are my key math terms and what do they mean? So it's a 6-year loan. So 6 is going to be my time. And it's $25,000. So $25,000 is my principal or my initial amount. And my interest rate is 4.5%. So that as a decimal, because I don't have a percent sign in the calculator, is 0.045. If the interest is compounded monthly, so monthly, how many times per year would it happen? Well, that would make n equals 12 because it's happening 12 times a year. What will he have paid? So that is looking for the total, so that's going to be the A, or the account balance, over the course of the loan. So that is what I am looking for. That's what the question's asking, is for A, when I know what N and T and R and P are. All right, so how do the variables fit into my equation? So I'm simply going to type them into my equation. So hopefully when you typed them in, you were able to get A equals 25,000 times 1 plus 0.045 divided by 12 to the 12 times 6. And we can go ahead and simplify that down. Let's go ahead and calculate what that would be. Now remember, it's 1 plus this value. If I just type that in straight into my calculator, it's going to do the division and then add it to 1, which will work, but I would just go ahead and do this piece and then add it to 1. All right, so hopefully you were able to find that it's going to be 25,000 times 1 plus 0.0375 to the 72nd power. And we can go ahead and ask ourselves, is the variable that I'm solving for in the exponent? No, it is not. The variable that I'm solving for is already isolated. So because it's no, I can just solve using my calculator. So I can literally just type that into my calculator and see what my answer is and what it means in context. And I end up with 32,732.5775. So to answer the question, over the course of the loan, Jack will have paid $32,732.58. So I just want to stop and point out a couple of things. So first of all, had you rounded this, because we're used to rounding to 3 decimal places. So had you rounded 1.00375 and you had made it 3.8, you would have been maybe off by a little bit. So when you're checking your answers on these, if you are off just by a few cents, that is a rounding error. So I don't want you to freak out about that. It will be very specific. One of the best things you can do, honestly, is to type this whole thing in all at one time and not necessarily simplify. I just like to use smaller numbers. But if I were taking a test on this, like my state TN Ready, I would type this whole value in because I'm using the true value. The other thing I want to point out is if I bought something and I borrowed $25,000 just for the cost of the item, and with the interest, I end up paying almost $8,000 more for it. So that's something that you need to think about. Is a boat worth paying another $8,000 over the course of 6 years? And that's why it's important to look at these compound interest problems and see, is the interest worth it? All right, so what I'd like you to do is I'd like you to pause the video and I want you to try number 7 on your own. Go through those questions, use those to answer this problem. All right, so with this one, hopefully you were able to come up with that the balance of the account after 12 years will be $6,358.48. Now, I'm guessing that if you had an issue, it came about with this word semi-annually. So if I have a semicircle, that means it's half of a circle, right? So semi-annually, annually means every year, so it'd be half a year. So how many times, if I'm compounding every half year, how many times in 1 year will it be compounded? That is twice. So semi-annually means twice a year. So when I plug all of that into my formula using 3.9%, N is 2, 12 years, $4,000 as the principal, my account balance will be $6,358.48. So what that means is that by investing in this account, after 12 years, if I only put in $4,000, I can make $2,400 off of the account. So interest can work both for you and against you, whether you're borrowing money or investing money. And that's why investing is so important. All right, go ahead and I'm going to have you pause the video and try number 8 on your own as well. Now, I want to clarify something because this was confusing to me as well. So this word bi-monthly. Bi-monthly has actually 2 meanings. If you Google it or look it up in the dictionary, some people say it's twice a month and some people say it's every 2 months. So for the sake of my class, we're going to refer to it as every 2 months. Bi-monthly, every 2 months, okay? So you may see bi-monthly, and I'm sorry, I don't have an answer as to why we can't clarify which this is, because compounding something every 2 weeks versus every 2 months is going to give us a very different answer. So, but for the case of this class, the sake of this class, I'd like you to think of bi-monthly as I'm compounding every 2 months. So my end value, what would that be over the course of a year if I'm compounding every 2 months? All right, so for this one, I got $24.97 is what he will earn in interest over 10 years. Now, I'm going to guess that if you got it wrong, it might have come about from the interest rate. If you notice, the interest rate is 0.8%. So that is less than 1%. So it's going to be less than 0.01 because I moved my decimal 2 places. And so 0.8% is not the same as 0.08 or 8%. So if you're ever confused about turning that decimal or that interest rate, that percentage, into a decimal, just take it, 0.8, and divide it by 100 because we know percent is out of 100. So when I plug that in, another place that you might have got off is the question is asking how much interest will he earn. So that $324.97 is his balance. So that's how much money is in his account after those 10 years. However, if we're looking at how much interest, he put in $300. He did not earn $324.97 in interest. So it's going to be that balance of $324.97 minus what he put in. And that tells me that he earned $24.97 in interest. Now, you may have gotten $24.98. There's some rounding errors happening in there, but if you are anywhere near $24 and in the upper end of the cents, if you're off by just a few cents, that means you just had a rounding error. But this question has a couple pieces to it that I think could have made a mistake, so we really have to pay attention to what is the rate as a decimal, and then what's the question really asking, and that's why I have that question built in here when you're thinking, which variable is the question asking for? Well, it's not really asking for A. It's asking for A after I subtract off how much money I put in. That will tell me what is the interest. All right, go ahead and pause the video, and I'd like you to try number 9 on your own. All right, so this is like the previous one in that it was asking how much interest will you earn. So I have to take into account the balance minus whatever I invested. So my principal is $750. It's an interest rate of 0.03. It's compounded weekly, which there's 52 weeks in a year. So after 20 years, when I plug everything in, I should have $616.35 in interest, because the account balance after 20 years will be $1,366.35, and then I subtract off that $750 that I invested, because that's not part of the interest, and that will give me that $616.35. All right, so now that we're comfortable with the compound interest formula, I want to apply a couple situations where it connects to this log unit. So it's going to be, we're going to have to use our knowledge of solving logs to solve these problems. So I'm going to use those exact same guiding questions in order to solve these, and it's just going to be slightly different when I get down here to the yes. If my exponent is the variable, then I'm going to solve using logs. So here we go. I'm going to read through and I'm going to analyze what are my key math terms, what variables do they represent, and which variable are we asking for. All right, so the first question is, how long does it take? Well, when I think about A, P, R, N, T, how long does it take? That's a measure of time. So what we're actually solving for now is we're looking for time. So that means we're going to be given everything else, including the output. So if I'm no longer given the input of time, that means I'm going to be given the output, or what that balance is after that certain amount of time. All right, so I immediately notice here's my percent. So that's my rate, and it's going to be 0.0635 as a decimal. I see that I'm compounded monthly. So monthly means 12 times a year. I see that I am inputting, or that is my principal, what I'm putting in is $1,000. And so I have T, I have P, I have N, and I have R. I have to have the output. So when I think about how long does it take to double, so double means twice as much. So if I put 1,000 in, I'm looking for when the output, when A is double. So if I put in 1,000, double would be 2,000. So that's when the output, or the balance of my account, is double what I put in. So what are the key math terms? What do they mean? And what am I solving for? So now I'm going to plug it into the formula. So now I know A. I'm looking for when is my account at $2,000. When I put in 1,000, oops, wrong color. And the rate is 0.0635. And I compound it 12 times in a year to the 12 times T. All right, so the variables fit in. So is the variable I'm solving for in the exponent? Yes, it is. It is in the exponent. I am looking for T. So that tells me that I've got to start peeling away until I get that T isolated. So the first thing that I notice is, I'm just going to use my algebra, is let's go ahead and get rid of as much as we can. So this whole value is being raised to the 12T. So let's get rid of this 1,000. So when I think about that 1,000 in relation to this value, it's being multiplied. So to get rid of it, I'm going to divide. So those will cancel, divide by 1,000, and 2,000 divided by 1,000 gives me 2. So 2 equals 1 plus 0.0635 divided by 12 to the 12T. All right, so I now have 2 equals some value being raised to the 12T. So let's go ahead and let's calculate what this value is. So I got 1.00529. Because it's such a small decimal, I went ahead and went out a couple extra. You don't necessarily have to do that, but I just at 1.0053 would be fine, but I don't know, I just wrote down 1.00529. So we're going to have slightly different answers if you were to round to 3 and I was to round to 29. To the 12T. All right, so I've gotten as far as I can. I can't isolate this any further because I can't get to that T because it's part of this base. So I have a value. This is in exponential form. I don't have any log in here. So in order to get to that variable, I'm going to have to utilize my knowledge of logs. So when I look back at my work, whenever I had a number equals a number to the variable and I'm solving for that variable, I'm going to utilize logs. So which form is it in? Is it in log form or is it in exponential form? Well, it's in exponential form because I don't have a log in there. So here is my base. So this base being raised to this power equals 2. So let's think about how we can rewrite logs or rewrite an exponential form into a log form. So it's going to be log, what is the base? 1.00529. Of what? Of 2 equals 12t. So that's just simply going back to rewriting the very first lesson, or I'm sorry, the very second lesson, that intro to logs. We took something from exponential form and we put it in log form. There is also another way to do it, and I just want to show that to you as well. So I can continue solving this way, or I could set it up. I'm just going to set it up over here. I could take the log of both sides. So I could take the log of 2 equals the log of 1.00529 to the 12t. All right, and so to simplify, whenever I have the log, I'm going to use the power property, and I'm going to bring that out front. So I really would have the log of 2 equals 12t times the log of 1.00529. So that's just simply utilizing the power property. And so then I'm looking at this. Where's my variable? Well, my variable is right here, t. And so I need to isolate t. So right now, t is being multiplied by 12 and by the log of 1.00529. So I can get rid of them at the same time if you'd like. If that's too much, I can go ahead and divide by the log of 1.00529 on both sides. And this is just basic algebra. It's just using different numbers than we're used to. So in my calculator, I can say the log of 2 divided by the log of 1.00529, and with that I get 131.3760, and that equals 12t. All right, well, how do I get rid of that 12? Well, I'm going to divide that. So t equals 10.948. So that's one way, using the properties, taking the log of both sides. I'm going to show you the other one. So if we remember back, right here, I can utilize the change the base formula. And we talked about that. If you don't remember that, I would suggest you go back and look. But it essentially says I can take the log of 2 divided by the log of 1.00529, and that equals 12t. And if you notice, we did that over here. The log of 2 divided by the log of 1.00529 equals 12t. So when I type this out right here, I end up with 131.3760 equals that 12t, and divide it by 12, and that gives me t equals 10.948. So then my last question is, what does my answer mean in context? So what that means is t represents time, so that means it's going to take about 11 years. I'm going to go ahead and round up in this case, because if I say about, I can clarify that it's going to be about 11 years, because this is pretty close to 11 years. So it will take about 11 years for the account to double. Okay, I realize that is a lot. I've just given you a lot of information. However, it's utilizing everything that we've done up to this point. So really, if you really were learning what we talked about before, you should be able to apply it one of the two ways. So this is simply, if you go back and look at solving log equations, this is going to look just like one of the problems that we've done. It just might have a little decimal with it, and we were used to like 5 to the 12t. The process is no different. So you really have to keep track of, what am I looking for? what do I have and how can I get to? So use those guiding questions that I gave you before when solving if you get stuck there. All right, let's do a couple more. All right, so again, I'm going to read it and I'm going to use these 3 questions to start with. So how long? Well, we measure that with time. So again, I'm looking for t. Will it take $30,000, so that's my P, to accumulate to $110,000. So that's going to be my account balance. So that's A. In a trust that earns 10%, so that's my rate, and that's going to be 0.1 or 0.10, compounded semi-annually. So semi-annually, twice a year. So I'm looking for time when I know all my other variables are given. So how do the variables fit into the equation? So A, which happens to be 110,000, is going to equal my principal of 30,000, 1 plus my R of 0.1 divided by how many times it's compounded, which is 2, to the n, which is 2 times t. So I'm solving for t. So is my variable in the exponent? Yes, it is. Well, we're going to have to use logs. All right, so the first step is I just need to look at what I have. So I have something equal to 30,000 times this value being raised to the 2t. So I need to isolate this right here, and I'll do that by dividing by 30,000. All right, so that will cancel. So when I do 110,000 divided by 30,000, I get 3.6667, I'm going to round, to equals, and I went ahead and calculated what this value is. So 1.05 to the 2t. So I have a number equals a number to a power. So this is exponential form. So now I can either rewrite it in log form and solve it, or I can use the change of base formula to solve it. It doesn't matter how you want to do it. I will solve it both ways. All right, so there's a lot of work, and I know I did it while you had it, or while I paused the video, but I wanted to have it all on so I could just explain it. So we got here, we have 2 ways. We can either take the log of both sides and solve it out, or we can rewrite this exponential form into log form. So I'll go ahead and explain this way first. So I took the log of both sides. That's all this is log of 3.667 equals the log of 1.05 to the 2t. Using the power property, when I raise something to the 2t power, I can just go ahead and put it out front and multiply it. So I end up with the log of 3.6667 equals 2t times the log of 1.05. So I just now have a basic equation to solve. I divided by the log of 1.05, and I got 26.6302 equals 2t, and then I divided by 2, and that gave me 13.3151. Over here, I rewrote this in log form. So log base, what's the base? So when I look at this, the base is what's being raised to something. So the base is 1.05 of this value equals the exponent. So then I use the change of base formula to type this in because I don't have a log 1.05 but base 1.05 button, but I can say the log of the big number divided by the log of the small number, the change of base formula. If you don't remember that, you got to go back and watch the video about change of base formula. That's why we did all that practice, so that we could apply it and it would be a skill that we just already know. Equals 2t, so when I did log of that divided by the log of 1.05, which we did over here, it's the same process, just a different approach to get there, and then divide by 2t, I still arrive at t equals 13.3151. So it will take a little over 13 years to earn that $110,000. And the reason I said a little over, because at 13 years, it won't. If you had said about 13 years, you can, but this 0.3 is almost half of a year. So however you word it, I don't think that that's going to be an issue on the TN Ready. But just be aware of ways that you can word so that you get your point across, but you're not having to say specifically, it will take 13.3151 years when you're doing these problems. All right, guys, we made it. I know this was a really long video, but I just wanted to make sure that we worked through all the examples together. So what are you going to need to remember? Where are errors? So did you get stuck? Like you were able to plug everything into the equation right, but you got stuck when it came to solving? Or where are you going to need to remember to look for what are hints or be sure to statements that you're going to leave for yourself? And lastly, what are 3 common mistakes you think students tend to make? What is your summary for yourself? So go ahead and write that in your notes. Maybe make a list of steps or just hints or suggestions to yourself when you're going back and studying. And what is your comfort level for this topic right now? So rate your understanding.